that the square root of 2 is an irrational number. That is, it cannot be expressed as a rational number in the form a over b, where a and b are integers, b not 0. So, some people go around and glibly say, oh, anything's possible. Well, not everything is possible. And perhaps we'll show today, although next time we'll be able to do it much more expeditiously with just like 2 steps. But perhaps we'll look at it today and see that there's no way to write the square root of 2. The square root of 2 is a number which, when squared, gives exactly 2. There's no way to write that as a fraction, no matter what numerator and denominator you use. And since a rational number is equivalent, if you do the division, a over b, if you actually do the division, you get what? You get a decimal. In fact, you get a repeating decimal. And so you can get close to the square root of 2 with a decimal. For instance, if you square 1.4, you'll get close to 2. If you square 1.41, you'll get closer to 2. If you square 1.414, right, 1414 is a 3 decimal place approximation of the square root of 2, you'll get even closer to the square root of 2. And the more decimal places you take, the better approximation you get to the square root of 2. And I can't tell if you're twirling something or raising your hand. I think you're just twirling something. It's okay. Once a student in class just sort of stretched a little bit, and I called on them, and they said, "No, I'm just stretched." And I said, "Well, you have to be careful. Like at an auction, if you raise your hand, oh, okay, sold." Anyway, so yes, so the more decimal places you take, the closer you get to the exact square root of 2, the closer you get to a number that squares exactly into 2, but you actually never get there. So maybe we'll take a look at that. So for now, let me shut off the video so that I can, let's just see. Okay, all right, getting there. It looks like 27 people here. Okay, so I have this stylus, this pencil stuck into here so that it should be compatible now. I should be able to use it. So I'm going to shut off my video. I still have to find out whether, I guess not, whether there's any way in which I can be writing to you and also see you, like maybe in a box or something. Also, this weekend, I'm sure that I will finally get to where I can share all our lessons with you, share all the recordings so you can go back and look at it. Nevertheless, let me recommend that even though all the notes will be there and accessible to you, I trust this very weekend, you gain something by taking notes as if you didn't have it recorded. Just the act of writing it imprints something on you. So I recommend, there may be some of you who just feel that you can learn better by listening and not being distracted by taking notes, then don't take notes. Other people may want to actually take notes, even though I'm writing the notes for you. So, all right, so here goes, one last time. So let's see, 9, another 9, another 9. Oh, well, okay. What? Oh, yeah, I can. Yeah, let's see. I think participants. Oh no, that's just a list of participants. More. How do I mute everyone? Oh yeah, okay, mute all. Okay, magic. Everyone's gone. Yeah, thank you for pointing that out. Okay, but if you do have a question, since I can't see you and I can't see if you're raising your hand, even inadvertently, just unmute yourself and ask the question if that occurs. Okay, so be back in a moment. I stop this video and then I go to more.
This meeting is being recorded.
Okay, it's being recorded, and so, okay. Okay, apparently it's already being recorded. All right, so share screen, then start broadcast. Okay, I have to wait a moment. And now I go out of this and press OneNote and okay, then I go to draw. Okay, so I've already set this up. Okay, so the homework consists of this. First of all, so this is in what I've called forms of integers. So I'm just continuing with the numbers. So question 11, so we've done the first 10, or at least I hope you've done the first 10. We'll probably go over some of it today. But I want you to do all this homework. Don't wait for me to do it. You have to do it. You learn by trial and error, and you learn by being frustrated when something doesn't come out, and then you take a little break and you try it again and you try something else, and you learn something by the trial and error. And I said this before, it's really important for you to attempt the homework and not be frustrated and give up. Well, you can be frustrated, okay, but don't give up on it. Keep doing it. So question 11 says, prove that the square of an integer that is not a multiple of 2 or 3. So you have to think about how you would represent an integer that's not a multiple of 2 or 3. Think of what that implies. If it's not divisible by 2 or 3, what does that say about it? And then show that you can write a number that is not a multiple of 2 or 3 in the form 24 times an integer plus 1. So that gives you a hint right there as to what form you're looking at. If you want to end up with something plus 1, you want to segregate the plus 1 so that you at least have that much. And in question 12, I just remind you what a prime number is. I think you know, but anyway, a number greater than 1, positive number, if it's positive, greater than 1, that has no divisors other than itself and 1. So, 2, 3, there they go, a number of them. And so the question is, what values can R have so that the set of numbers of the form 4n plus r will include all odd prime numbers? So remember, we talked about this. All the prime numbers are odd except 2. And so, as usual, n and r are integers. And question 13, this one is not easy. You're going to have a lot of trouble with it, and good, have a lot of trouble. Spend hours on it. Go away, take a rest, try something else. Prove by mathematical induction. The statement is very simple. A to the nth power minus b to the nth power is divisible by a minus b. A to the first minus b to the first. I've recommended that when you have a numerical question like this, you take a few examples, first of all, to convince yourself that it's true. You may possibly get some insight into it, but anyway, we'll talk about mathematical induction. For now, I press the pen, and thanks to one of you, I have a thin enough line, and then draw, so I guess, yep, okay, it's working. So let's erase the trial scribble. All right. Okay, so let me put this thing down horizontally so I can write. We're looking at the division algorithm, which really is the mathematical basis. Again, I'll prove the division algorithm in an airtight way next term, but for now, I'll content myself with showing a geometric depiction of it. And it is really the foundation of your being able to divide. So suppose we have okay, so suppose, let's start with A positive. So, okay, here's A, here's 0, and we're going to divide A by some Q. So here's 1Q, 2 times Q, 3 times Q, 4 times Q, and so on. And what we're going to do is put in, that's 4, we're going to put in as many of these Q's. So each one of these, the difference between these successive multiples of Q are Q, Q, Q. We're going to put in as many of them as fit into A, but there's no guarantee that an integral, again, integral means integer, a whole number, multiple of Q will exactly land over here on A. If it does, then A is a multiple of Q, and Q divides A, which is what we had on Tuesday. Q divides A means that there's a number, say B, such that A equals Q times B. But if not, so we keep on going, and eventually we're going to get to, say, B of these Q's, where we get to a point close to A, as close to A as possible, but not exceeding it with multiples of B. So this amount, after we get Q of, and of means multiple, means times. Let me move over this plus sign a little. So if you, that's a plus sign, believe it or not. So if you look at that diagram there, it should be clear that we can ultimately, by taking enough of these Q's, so this is B times Q plus that amount, which we'll call R, plus an amount R greater than or equal to 0. And as I say, if R equals 0, then you just have what I have over here, A equals B times Q, and that shows that A is a multiple of B. It's B times some integer Q. But otherwise, we're going to get as close to A as possible. And in order to get to A, it's going to be BQ plus an amount R greater than or equal to 0, and R is less than B. Why is R less than B? Because if it weren't, if it were more than B, you could squeeze in another B, so instead of B times Q, it would be B times Q plus 1, say. So yeah, you could squeeze in another one of the divisors. So for instance, if you're dividing, say, 29 by 3, and you say, okay, 29 equals 3 times 8, but then to get up to 29, 3 times 8 is only 24. To get up to 29, you'd have to add 5. Oh no, you're dividing by 3, so you can squeeze in another 3, another multiple of 3 into that, and instead of saying 29 equals 3 times 8, you can squeeze in another 3, so it becomes 9 threes. So you would write 29 equals 3 times 9 plus 2, which is what remains, called the remainder. It's what remains after you've done as much multiplication as you can. And so this equation becomes A equals BQ plus R, where R is greater than or equal to 0, but also less than B, again, because if it's not less than B, you can squeeze in another B into it. So if you look at this diagram, and it's a reasonable geometric depiction of what's happening, you can always get up to A with a certain whole number, integral number of divisors, b, and then add a remainder. And just for uniformity, we'll do the same thing if a is negative. So like if this is 0, so let me call this negative a. So you do the same thing. Here you'd have negative 1b, negative 2b, etc. But this time, again, for uniformity, so we can make r over here, r greater than or equal to 0. We're going to go a little past, as little as possible, past a. So let this be the, let's say, the first multiple. Why is this writing darker now? Am I pressing harder? Let me go to the pen. No, it's still showing. All right, maybe I'm just pressing harder. The first multiple of b, oh there, that's better, of b that is less than in other words, the way I'm drawing it to the left of negative a, so that you can get back up to a, moving to the right, this way, and moving to the right gives you an r greater than or equal to 0. Again, if it's equal to 0, then you land, as you take these b's to the left, you land exactly on negative a, and negative a is a multiple of b. But if not, you go just a little to the left of it, the first number of b's possible, just one b to the left of that number, negative a. Or you could just call it a, but then say a is negative. I put a negative in front of it to help you visualize it. So you can still make r positive. So, so you take the first multiple of b that's less than to the left of negative a, so that you get up to a by moving to the right. That is by adding a positive remainder r. And so in every case, we have a equals b q plus r, where 0 is less than or equal to r, is less than, strictly less than. Because if we're equal, you could squeeze in another b, less than. And if you look at the second diagram, if b happened to be negative, you still want r to be less than that divisor, because then you could squeeze in another one. And so to cover that, should b be negative, we'll say that. And this, including the inequalities at the end, is called the division algorithm, and including the inequalities. Let me go back to the last class because I think I showed you the actual division there. Yeah, okay, down here. Right, so I showed, there it is, 2 into 7 equals the quotient 3 on top, the partial quotient, then you multiply back, and then if you look to the right of this, so you can see what I'm seeing. I mean, you've told me that you can see what I have. So I pulled up yesterday's lesson. Okay, so then you can see next to the numerical example, I did it with A and B and Q and R. So yeah, that's why it's actually called the division algorithm. It tells you how to do division, elementary school division. Okay, so then I gave you some examples that I hope you looked at. You're really not going to get this by watching me do it. So I asked you to actually numerically write the statement of the division algorithm. If A equals 23 and B equals 3, and so we can write this as 23. That's over here, the thing that I have the brace under it. See where it says A equals BQ plus R. So I want to express 23 in the form B, where B is 3, times some Q plus R, where the R is less than or equal to the absolute value of 3, which is 3. So we have that 23 can be written as 20, let me write it as, so it's in the form B since I'm dividing by B. Let me put the B first, which is 3. So it's 3 times 7 plus 2. Now what happens if A is, like in the second diagram above, negative 23, but B is still positive 3. What's that going to look like? So now we're going to write negative 23. That's your A. There it is. A equals negative 23. And then we'll write, so the divisor is 3. And now we have to go a little to the left of negative 23. And that would be as little as possible to the left. Negative 8. So that's negative 24, and now to get back up from negative 24 to A, which is negative 23, you add 1. In the third case, this time A was still positive, but B was negative. So this time we'll write 23, that's your A, equals, and now your divisor is negative 3, so we have to multiply by something, and we want to get to positive 23. Well, we have a negative 3 there, so to get to a positive number, we're going to want a negative there. Now, if you take a look at that a moment, if you multiply by negative 7, that gives you positive 21, and then we can get up to 23 there by adding 2. And finally, if they're both negative, if A is negative 23 and B is negative 3, then we can write that negative 23 can be written in the form negative 3, that's B, negative 3 times what? Well, negative 3 times negative 7 isn't enough because we want the remainder to be positive. So for a negative number, we have to go a little to the left of that negative number, and that would be 8, that's negative 24. And now, as before, on the second line, to get up from negative 24 to negative 23, we will add 1. So notice that in each case, R is strictly less than the absolute value of B, which is the absolute value of either positive or negative 3, depending on which it is, but the absolute value of positive or negative 3 is 3. So R is less than 3. And look at the R's. They're all less than 3. They're either 1 or 2. They're less than 3. So that's the kind of thing I'm talking about. This has ramifications. I mean, so far, I've just introduced it as the explanation for division, which is an important operation. By the way, remember we defined subtraction and division in terms of the, you might call them the principal or fundamental operations. So recall definitions of subtraction and division. A minus B equals by definition, colon equals A plus the additive inverse of B, which we have by the fourth property of a ring, and A divided by B by definition is A times the multiplicative inverse of B. I don't suppose anyone can guess the next 3 words I'm going to write. Okay, I'll write them. If it exists, right? So first of all, 0 never has a multiplicative inverse, because what does the multiplicative inverse of a number have to do? It has to multiply that number to give 1, and 0 times no number gives 1, because we proved that 0 times any number is still 0. And in the integers, we've already looked at this, numbers like 2 and 3, and in fact, any numbers other than positive and negative 1 don't have multiplicative inverses. So, so we can't, in general, do division in integers. Anyway, right, that's just to remind you, though. I mean, the definition is still the definition. It doesn't apply to our particular venue of the integers, but it is a definition. So if you're in a place, and one of you mentioned the idea of a field, if you have, for instance, a field where you do have inverses of non-zero elements, then you have that definition. Okay, well, first of all, at this point, does anyone have any questions other than about the homework? I would like to get to the homework, but first I'd like to talk about proof by mathematical induction. But does anyone want to stop me right now and ask any questions? If not, at the end, before we conclude the meeting, I'll do what I always do, shut off this, it's called OneNote that I'm writing to you on, and get back and see you a little bit and talk to you. Okay, so if there's nothing in particular, and again, what we've done so far is not difficult, but it does start building up rather rapidly. So please try to keep up with it. Let's talk about mathematical induction. Often in mathematics, if it's understood that it's mathematical induction, sometimes the adjective mathematical is left out. Sometimes you say just, give an inductive proof, it means mathematical induction. And let me just say something in passing about that. In deduction, you I'm talking about deduction now, you start with a general principle and apply it to an individual principle, such as, I don't know, if you say that the sum of two even integers is even, then from that you can deduce that 6 plus 98 being two even integers would be an even integer. Induction goes the other way, and it is what's used in science. And how do you determine a law in science? You do it by observation of many cases, and from that induces, it creates induction, that induces a general principle. So, for instance, if you try a lot of different things, hold them up and let go of them, they all fall, then you, from that abundance of examples, you infer a general principle. And that is what science does, and it ordinarily works very well, but it's not a mathematically airtight proof. I suppose the only time you have a mathematically perfect proof is in mathematics. But if you perform enough experiments, you can see that, all right, it always seems to work that way. In mathematics, that would not be a proof. We don't try a lot of examples of adding two even numbers and saying, oh, it looks as if every time I add two even numbers, I get an even number. That's not considered a mathematical proof. And there are many examples which I could give you. I don't have right in front of me. For instance, I believe n squared minus n plus 41 is a prime number for n equals 1, 2, 3, 4, 5, 6, but obviously not for 41 itself. N squared minus 41 plus 41, when n is 41, obviously is not a prime number. It's 41 squared. It's divisible by 41. I have another example that I have in the next room. I won't take time to run over and get it, where something holds, I think it's numbers with the number of prime factors, with an even number of prime factors exceeds the number of numbers. I can get this for you eventually and tell it to you. With an odd number of prime factors, it works all the way up to, as I recall, 5,775, and then all of a sudden it breaks down. Why? What happens? So there's a long string. I once gave a lecture, I actually have the notes for it, called Patterns That Don't Continue. And what I did was I collected a lot of, patterns that don't continue. In fact, if I think of it later, which I probably won't, maybe I should write it down. I can give you, I'll write it down. I can give you a very simple example of a pattern that works as far as you want, for up to 1,000, up to 1,000,000, whatever you want. Very simple example, but that doesn't prove that it always works. So mathematical induction is a different kind of proof. It's an actual mathematical proof. And what it says is this. And so again, we are taking this as a, quote, known part of arithmetic. Namely, it really comes from the closure property of addition. If you have any integer and you add 1 to it, you get another integer, you get the next higher integer. So what it says is, it's essentially counting. It says, if, say, S, I think I've used that symbol. If not, S is a subset of this fancy N. What does that mean? It means that, I'll write IE, that is, So if S is a subset of N, what does it mean to say A is a subset of B? It means that everything in A is also in B. So for instance, the set of people in New York State is a subset of the set of people in the United States because everyone in New York State is in the United States. So that's what a subset means. Every A is a subset, and that thing that looks like a C, it's not actually a C. It's a, just as the union is not really a U, a U, it's more like that. An intersection is like that. And that symbol, it's not really a C. You can think of it as a C standing for contained in, but so it means that every element of S is an element of N, but who's in N? The natural numbers are N. So this is a way of saying that every element, every number, every element of S is, it's contained in the set of natural numbers. So who's in the set of natural numbers? Natural numbers are. So saying S is a subset of the set of natural numbers means that every element of S is a natural number. And as we had on the first day, a natural number is a counting number, a number that you use in counting. Namely, that's not a minus sign or a negative sign, it's a dash. 1, 2, 3, 4, and it keeps on going. Then, if 1 is contained in this subset of the natural numbers S, and let me write this in two ways. So what this really means, so I've written it as K, that's really meant to be a lowercase k. So there's an uppercase, no, there's an uppercase K, that's a lowercase k. And also that's an uppercase U, but a lowercase u has this sort of this tail on it. Anyway, so this says K is an S implies K plus 1 is an S. I mean, some of you have seen proof by mathematical induction before, particularly if you've taken mathematics 4000 or 4009, or maybe elsewhere. Actually, I learned this in high school. Maybe some of you did. So this says K is an S implies K plus 1 is an S. Remember that that double arrow is equivalent to if then. So another way to say that is if K is an S, then K plus 1 is an S. Or to put it another way, whenever the number, let me put it this way, whenever one number, K, whenever one number, of course, number means integer, then the next number, next integer. So look at what this is saying. I guess I'll finish this if then statement. So if this is true, then S is not a proper subset of n, S actually equals n, meaning S contains all of the natural numbers. And as I say, I'll actually prove this axiomatically next term, but let's look at it for now. I said a moment ago that this is really a counting process. So why? Well, by hypothesis, that's what you're starting with. That's what's given. 1 is an S. But the second statement says that whenever one number is in S, the next number is an S. Over here at the top, if K is an S, K plus 1 is an S. That is, whenever one number K is in set S, then the next number K plus 1 is an S. So it says that whenever one number is an S, the next number is also So now, since we had over here, I just underlined it, 1 is an S, so now we get that the next number, 2, is an S. And then similarly, likewise, as you go ahead, but now, since 3 is an S, the next number, 4, is an S, etc. Every natural number is an S. So as I say, it's really a counting process. You start by saying 1 is an S, and then the next number is an S. That puts 2 into S. Oh, but now 2 is an S, so the next number is an S. 3 is an S. Oh, so 3 is an S, the next number is an S, 4, and so on. So you're actually counting out the numbers. Let me mention, if you start with a number other than 1, I don't know, say, 6, for whatever reason, and we'll see some reasons, then all natural numbers starting with 6 in the same way. So you're saying, okay, 6 is in the set, then the next number 7 is in the set. Since 7 is in the set, the next number 8 is in the set, and so on. In most cases, we'll start with 1, but we'll definitely see cases where this situation or concerning or about. So this is going to be a method of proof of a statement about natural numbers. To show, and by the way, the statement, as usual in mathematics, can be given in terms of symbols. It doesn't have to be in terms of words, but if it involves a natural number, n, whether you say it in words or in mathematical symbols or a formula or an equation, it's still a statement involving natural numbers. So to show that a statement, again, however the statement is rendered, to show that a statement about natural numbers is true for all natural numbers. And again, if for some reason, and we'll see reasons, if for some reason you're not actually starting with 1, you're starting with 2 or 3, then it would be from there on. So to show, so let's finish writing this and then we'll take an example. And then it's 20 to 7. I would maybe like to go over some of the homework. To show that a statement about natural numbers is true for all natural numbers, or just those natural numbers starting at a particular number show or establish one way or another that the statement is true I don't want to keep saying natural numbers. Let's give it a name. So over here, to show that a statement about natural numbers n. All right, so n over here, to show that a statement about natural numbers, call it n, is true for all natural numbers, or just those starting with a particular number, show or establish that the statement is true when or for n equals 1. All right, so now it's true, and that will usually be by direct computation, but however you do it. Okay, so next, I want to be careful about how I say this, because you're taught not to make assumptions in mathematics. And I could avoid using that word by consolidating what I'm going to show as 2 steps into 1 step. I'll do both. So first I'll say it in 3 steps. Suppose the statement, to avoid using the word assume or suppose, that just means you're going to use it. The statement is true for any natural number k. 3, use that assumption, and again, I'll say a little more about this word assumption. And this assumption is called the inductive assumption, or inductive hypothesis. So a hypothesis is something that you're just using. You know, the Greek prefix hypo, it means under or less than, and a thesis is something that you're propounding. So a hypothesis, a hypothesis. Hypo is under, hyper is over or more than. The inductive hypothesis. So use step 2, that assumption, that hypothesis, to prove it's really hard to write on this slippery glass. That the statement holds, is true, is valid for, or you might say when, n equals k plus 1. So this is the step up step. So you're stepping it up from n equals k to n equals k plus 1. Now, if you don't like the idea of, at the beginning of number 2 above, assume, so I'll just say 2 and 3 together.
Professor?
Yeah.
Is that a lowercase k or is it a capital K?
Oh, I'm using lowercase k's here. Oh, yeah, there's not a, you have to write very carefully. I mean, in print, it's very clear. I'm only using lowercase k's. I will, should I say always? There might be some exceptions, but I can't think offhand really of where I would be using uppercase letters, except for these fancy letters that I showed you, like that, or this for the integers, or this for the rational numbers, or this for the real numbers, or this for the complex numbers. But those are distinctive and distinguishable. No, we usually reserve capital letters for whole sets and lowercase letters for elements of the set. So yes, when I'm talking about just numbers, I'm using lowercase letters.
Okay.
You know where the terminology lowercase and uppercase comes from, as opposed to capital letters. Sort of the official name of small letters are minuscule letters. Minuscule, by the way, is spelled M-I-N-U-S. It's not mini, it's minuscule. And capital letters are majuscule, M-A-J-E-S-C-U-L-E. But lowercase and uppercase, in the old days of printing, when it was called letterpress, where they actually had letters stamped out on pieces of lead, because lead is soft enough and has a low enough melting point or softening point, even though it's toxic, of course, including the fumes. So they actually constructed, in the earliest printing presses, And actually, up until, I guess, linotype machines started doing it automatically, where you could just type in a word and it would choose the letters. Printers actually had to go to cases, boxes, called cases, that had the individual letters. And because the small letters were in more use, they were in the lower case, the lower part of the case, a case closer to the person who was composing the text, and in the uppercase were relegated the capital letters. So that's lowercase and uppercase. Anyway, so 2 and 3
That's
together
interesting.
say, yeah, it's you know, the Nobel Prize, the American Nobel Prize winning physicist who died just a few years ago, Richard Feynman, said everything's interesting if you look deeply into it, deeply enough into it. And he gave an example. I don't remember the details, but it was something like someone is late for a meeting or something. Well, why were they late? Well, it was snowing. They slipped on the ice. Oh, well, what made them slip on the ice? Did they have a horizontal vector from their motion, and which kept them sort of going when you have no traction? And then okay, maybe you have that, but still, ice is a solid. Why did you slip on the ice? Oh, the ice is smooth. Well, what does it mean to say the ice is smooth? Well, actually, a crystalline structure like ice has a reduced melting, let's see, reduced, increased melting point, right, with pressure, which is why, for instance, if you ice skate, you're actually gliding along, not on solid ice, which, well, is a solid, like skating on the floor. No, it's actually melting a small amount of the superficial ice, and you're actually gliding along on water, on a slight bit of water that acts as a lubricant with the ice. So then he went on and said, well, okay, so what is it in the constitutional molecular makeup of the ice that allows that to happen? And then, why does it happen? And so water actually has special properties that are very unusual, having to do with the 135-degree angle between the two hydrogen atoms attached covalently to the oxygen. And so, that's what he meant. Look how complex it gets. It gets into ultimately the quantum level. So we won't go that deeply here, but it is interesting to know what lowercase and uppercase mean. Okay, so
Wow.
so yeah, you know what? The world is complex. Not everything's understood, but you know what? That's what makes life interesting. If it's an open-ended book where there's always more to know, more to understand, deeper understanding to get. And that's what your education is doing for you. And I hope it really is doing that for all of you in everything you study. I've never said mathematics is the most important subject. It's very important. Science is very important. Philosophy is important. Poetry is important. Literature is important. Foreign language is important. History is important. Political science is important. Economics is important. Everything you take adds to who you are, and eventually, hopefully, makes you into an educated person. Which, to quote an interim president we had of Baruch College some years ago, President Lois Kronholm, Kronholm, she pronounced it actually. She said that her goal for the college is to make students into interesting people who are interesting to others because they're just interesting to talk to, but also, tellingly, she said, interesting to themselves. And that's a really important thing. People who experience the life of the mind, well, they're never bored. They always have something that they can think about. And I trust that all of you are well on your way to that. But it's an enterprise that occupies an entire lifetime. So 2 and 3 together say that whenever the statement is true for one number, it's true for the next number. So again, it's really a counting process. So, okay, so putting 2 and 3 together like that avoids the use of the word assume, but you know what? You can assume anything you want. It may or may not be true. I mean, you can assume that, I don't know, it's December now and tomorrow's Christmas. You can assume that it's wrong for the time being. It'll eventually be right. So you can assume that, but you're assuming it in the service of proving something, namely proving that you can step it up to the next number. Let's give an example. Let's start with this example so you can see what I'm talking about. So the story is told that Gauss, Carl Friedrich Gauss, whose name pervades number theory, complex analysis, he was just a remarkable, if rather unpleasant genius. I say unpleasant because he wasn't interested in helping students. He hid his results and sometimes didn't publish them, so other people got credit. But Gauss and I guess the second half of the 1700s, I guess he was, or was it the first half of the 1800s, maybe? And Sir Isaac Newton, who developed calculus and basically gave us quantitative physics and elucidated the world, at least the macroscopic world. Within the past 150 years, steps were taken to understand the world at the submicroscopic, the subatomic level. But you know, Newton's laws of motion, he just put physics and the laws of nature on a mathematical basis. And in antiquity, that means a long time ago, Archimedes, those three are considered the three most eminent mathematicians in history, Archimedes, Newton, and Gauss.